the data started coming back before the crew did. That is how it always works in deep space missions. The telemetry stream and the science instruments and the recorded observations flowing back to Earth through the deep space network antennas in the hours and days after the mission, while the astronauts are still doing the work of coming home, still managing the re-entry procedures and the parachute deployment and the recovery sequence that ends every crewed space in the controlled drama of a splashdown in the Pacific Ocean. The mission controllers and the science teams at Johnson Space Center and at the research institutions that had contributed instruments or investigation objectives to Artemis II were already processing the early data while the crew was still in the water, still being helped aboard the recovery ship, still blinking in the unexpected brightness of the Pacific afternoon after 4 days in a vehicle whose windows frame a sky that is not blue. And what the data was showing in the initial processing that began within hours of the mission's end, and that deepened over the following days as the full dataset was downlinked and organized and began to be analyzed properly, was producing in the measured language of scientists who are trained to be careful about what they claim before the analysis is complete. A series of findings that none of them had expected to be quite as clear or quite as significant as they were turning out to be. The radiation environment at 250,000 miles from Earth was not a surprise. In broad terms, the scientists who designed the radiation measurement suite aboard Orion had built their instruments around models of the deep space radiation environment that had been developed over decades of unmanned spacecraft observations, refined by the measurements from the Apollo missions, and updated by subsequent robotic missions that had passed through or operated in the cislunar environment. They expected elevated radiation compared to low Earth orbit. They expected to see the signature of galactic cosmic rays, the high-energy particles that stream into the solar system from outside it, and that the Earth's magnetic field and atmosphere shield us from on the surface. They expected to see the variable contribution of the sun in the form of low-energy solar energetic particles. What they did not fully expect was the degree to which the passage through specific regions of the cislunar environment produced radiation, signatures that the models had underestimated in ways that were going to require a fundamental revision of the assumptions built into the planning for longer duration missions. The discovery did not announce itself dramatically. It accumulated data point by data point across the 4 days of the mission, and it was only when the full dataset was assembled and the initial analysis was completed that the magnitude of the discrepancy between the model predictions and the actual measurements became fully apparent to the team. That discrepancy is one of several things that Artemis II discovered during its lunar flight that the mission was not specifically designed to discover. Findings that emerged from the combination of instruments, observations, and the simple, unprecedented fact of having human beings and a human-rated spacecraft in the deep space environment beyond Earth's magnetosphere for the first time since 1972. The mission was designed as a test flight, a verification that the Orion spacecraft and the Space Launch System and the ground systems and the operational procedures all worked together as designed in the actual environment they were built for. It was not designed as a discovery mission in the way that a dedicated science spacecraft is designed around a specific set of measurement objectives. But the history of exploration is full of the pattern that Artemis II is now embodying. The pattern in which going somewhere new produces knowledge that nobody knew to look for, because the act of being there reveals things that the models in the prior remote observations had not fully captured. This is the story of what Artemis II found at 250,000 miles from Earth, and why some of it is changing the way the people planning the missions that follow it are thinking about what those missions will require. The cislunar environment, the region of space between the Earth and the Moon, is one of the most scientifically important and most practically consequential volumes of space that human beings will operate in during the coming decades of exploration. It is the highway between Earth and the Moon, the medium through which every crewed lunar mission must travel. And it is the region that future infrastructure, including the Lunar Gateway space station, and the propellant depots, and communication relay satellites that will support sustained lunar operations, will inhabit. Understanding the cislunar environment is therefore not simply a matter of scientific curiosity. It is a practical requirement for designing the systems and the mission profiles that will keep astronauts safe during their journeys to and from the Moon. The difficulty is that the CIS has been poorly measured by human-occupied spacecraft since the end of the Apollo program in 19. The unmanned spacecraft that have passed through this region on their way to other destinations have provided measurements of specific parameters, particularly the radiation environment, as seen by instruments that were not designed with human health as their primary concern. And the data from these missions has contributed substantially to the models that mission planners use. But the specific combination of measurements that is needed to fully characterize the environment for human spaceflight purposes, the integrated radiation dose, at the locations within a spacecraft where astronauts are positioned, the shielding effectiveness of the actual materials that make up the crew compartment under realistic operational conditions, the correlation between the space weather conditions measured by instruments outside the spacecraft and the dose measured inside. These measurements require a human-rated spacecraft in the actual environment, and they had not been made in the cislunar environment since the final Apollo mission. Artemis I, the unmanned test flight that preceded Artemis II, carried radiation measurement instruments and returned data that substantially improved the characterization of the cislunar environment. The Matryoshka asteroid radiation experiment, which flew on Artemis I, and which used anatomical phantoms, mannequins instrumented with hundreds of radiation dosimeters, positioned throughout their bodies to simulate the radiation dose distribution within a human astronaut, provided the most detailed characterization of the deep space radiation environment inside the Orion spacecraft that had been achieved since Apollo. The data from Artemis I was incorporated into the planning for Artemis II and informed the predictions of the radiation exposure that the crew would experience. What the Artemis II radiation measurements revealed was that the Artemis I data, as valuable as it was, had not fully captured the variability of the radiation environment that the crew would actually experience. The cislunar radiation environment is not uniform. It varies with position in the trajectory, with the specific regions of the Earth's magnetic field, and its transition to the unshielded deep space environment, with the instantaneous state of the sun's activity, and with the complex geometry of the spacecraft's orientation relative to the incoming radiation field at any given point in the mission. The instruments aboard Artemis II, which were designed to operate continuously throughout the mission and to correlate the crew's position within the spacecraft with the radiation measurements at their body, captured this variability in a way that the Artemis I phantom measurements could not fully replicate, because the phantoms could not move around the cabin, could not position themselves in the way that actual astronauts do during the different phases of a mission, and could not provide the subjective reports about activity and positioning that the crew members contributed to the dataset. The specific finding that has most directly affected the planning for subsequent missions is the characterization of the radiation environment during the passage through the outer portions of the Van Allen radiation belts on both the outbound and inbound legs of the mission. The Van Allen belts are regions of trapped charged particles held in the Earth's magnetic field, and they represent the most intense radiation environment encountered during a cislunar mission. The inner belt, centered at roughly 1 to 2 Earth radii altitude, contains high-energy protons that are produced primarily by the interaction of cosmic rays with the atmosphere. The outer belt, centered at roughly 3 to 7 Earth radii, contains high-energy electrons that are accelerated by processes in the magnetosphere. Spacecraft transiting to and from the Moon must pass through both belts, and the transit time and trajectory through the belts affects the total radiation dose accumulated during this phase of the mission. The Artemis trajectory was designed to minimize the time spent in the most intense parts of the radiation belts, and the dose accumulated during the belt transits was within the expected range based on the pre-mission models. What the data revealed was a specific feature of the outer belt environment during the outbound transit that the models had not predicted with the fidelity that the measurements showed. In a particular region of the outer belt that Orion passed through approximately 4 hours after the translunar injection burn, the electron flux at the energies most relevant to the shielding design of the crew compartment was elevated above the model predictions by a factor that, while not posing an immediate additional health concern for the Artemis II crew, whose total mission duration was short, would represent a meaningful cumulative dose contribution for crews on longer missions. The elevation was persistent across multiple consecutive measurement intervals, suggesting that it was not a transient enhancement associated with a specific space weather event but a feature of the belt structure in this region during this phase of the solar cycle. The team that is analyzing the radiation data from Artemis II has been comparing the measurements to the operational models that are used for mission planning, and the comparison is driving a revision of those models that will affect the specific trajectory parameters of future Artemis missions. The revision is not large in the sense of requiring a fundamental redesign of the mission architecture. The Orion spacecraft and its shielding design retain adequate margin for the corrected radiation environment, but the revision is real and significant in the sense that it demonstrates the value of the Artemis II measurements and the principle that the actual environment encountered by an actual spacecraft with an actual crew contains information that models built on prior data cannot fully capture. The Lunar flyby itself, the passage of the Orion spacecraft around the far side of the Moon, on the trajectory that took the crew to the record distance, and then began the return journey, produced observations that the mission had not been primarily designed to make. The Orion capsule was equipped with cameras, including external cameras designed to capture imagery of the spacecraft and its lunar environment for operational and documentation purposes, and these cameras recorded the lunar surface during the flyby at a resolution and from a perspective that added to the existing database of lunar imaging in ways that the science community is still processing. The specific region of the moon that the Artemis II trajectory brought the spacecraft closest to is the lunar south polar region, the same general area where Artemis III is planned to land. The proximity of the flyby trajectories to the South Pole was not accidental. The mission profile was designed in part to provide a first-person reconnaissance of the lunar south polar region from a crewed spacecraft, giving the crew and the mission planners a perspective on the terrain and the lighting conditions and the visual appearance of the region that could not be obtained from orbital imagery alone. Because the specific character of the terrain as seen from a spacecraft at operational altitude and trajectory is something that orbital images, no matter how high their resolution, do not fully convey. What the cameras recorded during the South Polar flyby is contributing to the detailed landing site assessment for Artemis III. The South Polar region of the Moon is characterized by some of the most extreme topography on the lunar surface. The permanently shadowed craters, which are the locations where water ice has been confirmed to exist by earlier robotic missions, are surrounded by crater rims and massifs that cast shadows extending many kilometers across the crater floors. The transition between the illuminated surfaces and the permanently shadowed regions is abrupt in a way that has important implications for the operations of a surface crew who will be moving between lit and shadowed terrain. The Artemis II crew's observations of the South Polar terrain, which they recorded not only on the cameras, but in detailed verbal descriptions logged during the flyby, are being integrated into the landing site selection process in ways that will directly affect the decisions about exactly where Artemis III sets down. The specific observations about lighting conditions are among the most operationally significant. The South Polar region of the Moon is illuminated at extremely low angles for extended periods around the summer solstice at the lunar South Pole, and the combination of bright illumination at shallow angles and the nearby deep shadows of the permanently shadowed craters creates a visual environment that is unlike anything that astronauts train for in simulations and analog environments on Earth. The crew's descriptions of the visual appearance of this environment during the flyby, the way the low-angle illumination creates long shadows that extend from every surface feature and complicate the visual perception of terrain, the way that the dark floors of the shadowed craters appear as absolute blackness against the brightly lit surrounding terrain, the way that the spacecraft itself casts a shadow that the crew could observe on the lunar surface at certain points in the flyby, are contributing to the development of the operational procedures and the training scenarios that will prepare the Artemis III crew for the visual challenges of operating in this environment. The farside communication blackout that the Artemis II crew experienced during the lunar flyby produced a dataset that was not explicitly planned as a science investigation, but that is turning out to be scientifically and operationally significant. During the 23 minutes that the spacecraft was behind the Moon and out of contact with Earth, the Orion communications system was monitoring the radio frequency environment around the spacecraft and recording data about the transition from the continuous communications link with Earth to the blackout and back. This data is relevant to the design of the communications relay infrastructure that will support sustained lunar operations, because the farside blackout and the approaches to it represent the most challenging communications scenario in the cislunar environment. The data from the blackout transition revealed features of the communications environment in the lunar vicinity that the relay system design will need to account for in more detail than the pre-Artemis II models had captured. The gradual degradation of the communications link as the spacecraft approaches the limb of the Moon, the point at which the line of sight to Earth is blocked by the lunar disk, does not follow a simple geometric progression. The actual signal quality metrics measured by the Orion communications system during the approach to blackout showed variations that are consistent with multipath interference, the phenomenon in which the direct path signal from Earth and reflected signals from the lunar surface arrive at the spacecraft antenna simultaneously and interfere with each other, alternately, constructively, and destructively, producing a rapid variation in signal quality that the models had not fully predicted. This multipath interference is relevant not primarily for the Artemis II mission itself, which successfully maintained communications throughout the approach to blackout and was not operationally affected by the signal quality variations. It is relevant for the design of the communications and navigation systems that will support the Lunar Gateway, the orbital station that will serve as a hub for lunar surface operations in the sustained phase of the Artemis program. The Gateway will spend portions of its orbit in the vicinity of the Moon, where multipath interference from the lunar surface will be a feature of the radio frequency environment, and the characterization of this interference provided by the Artemis II data will inform the design of the Gateway's communications systems. The blackout period itself was one of the aspects of the mission that the crew described with the most detailed and the most emotionally significant observations. The 23 minutes of absolute communications isolation, the longest communications blackouts experienced by any crewed spacecraft since the Apollo Farsight was described by each crew member in terms that were consistent in their emphasis on the particular psychological quality of the experience, but that differed in how they articulated its significance. The commander described it as the moment when the mission became fully real to him, when the abstract knowledge that they were on the far side of the moon, a fact he had known intellectually since the mission planning began, became experientially concrete. The pilot described it in terms of operational focus, the way that the absence of the continuous background presence of mission control concentrated his attention on the spacecraft systems and the crew's own resources in a way that had an unexpected clarity to it. Christina Kuch, who had spent more time in space than any other member of the crew, and who had experienced the psychological dynamics of long-duration spaceflight ostensibly, described the blackout in terms of the specific quality of the silence that accompanied it, not the absence of sound, which spaceflight always provides, since the vacuum of space transmits no sound, but the absence of human voice from the ground. The specific silence of being genuinely alone in a way that even the remote location of the International Space Station does not produce, because the station is always in communication range. These observations have been incorporated into the psychological research program that the human spaceflight medicine community has built around the Artemis missions. Because the psychological experience of communication isolation is one of the most important human factors considerations for missions to Mars, where communication delays of up to 20 minutes one way will make the continuous communications link that characterizes Earth orbital and cislunar missions impossible. The Moon, with its roughly 3-second one-way communication delay and its relatively brief, far-side blackout periods, is the nearest available analog for the communication isolation that Mars missions will require crews to manage. What Artemis II's crew experienced during the lunar far-side blackout is the first data point in a series of measurements that will build toward an understanding of how human beings psychologically manage the transition from continuous communication to genuine isolation, and what operational and design decisions can best prepare them for that transition. The life support system performance data accumulated during the Artemis II mission is among the most practically significant results of the flight from the perspective of the engineers who are designing the systems that will support longer duration lunar surface missions. The Orion life support system kept 4 astronauts alive and comfortable in the deep space environment for 4 days, performing every function that it was designed to perform. But the engineering significance of a system test is not limited to whether the system passed or failed. It lies in the detailed performance data that reveals how the system actually operated in the real environment. Data that can be compared to the predictions of the design models and used to refine those models for future applications. The carbon dioxide removal system, which is one of the most critical life support components aboard a crewed spacecraft, uses a chemical sorbent to capture carbon dioxide from the cabin air before it builds up to levels that would harm the crew. The performance of this system during the Artemis II mission was nominal in the operational sense that the cabin carbon dioxide levels were maintained within the acceptable range throughout the mission, but the detailed performance data shows that the sorbent consumption rate during the 4th day of the mission, when the crew was engaged in the highest activity levels of the flight in preparation for the return, was somewhat higher than the preflight model had predicted. The discrepancy is small and within the design margins of the system, but it is a real signal in the data that the life support engineering team is now using to refine the consumption rate models that will be applied to the planning of longer duration missions. The significance of this refinement is not that it reveals a problem with the Artemis II life support system. It reveals a small deviation between model prediction and actual performance that, if uncorrected, would accumulate into a meaningful uncertainty over the duration of a longer mission, a lunar surface mission of 30 days, which is within the range being discussed for the later Artemis flights, would accumulate 30 times the total carbon dioxide production and sorbent consumption of the 4-day Artemis II mission. A model that underestimates the consumption rate by a few percent on a 4-day mission would underestimate it by a few percent on a 30-day mission as well, and the absolute magnitude of that underestimation would be much larger. The Artemis II data provides the opportunity to correct the model before the longer missions fly, rather than discovering the deviation during a mission, when the consequence of an underestimated consumable margin could be operationally significant. The same principle applies to the water recovery system, the thermal control system, the power management system, and every other life support component aboard Orion that generated performance data during the 4-day mission. None of these systems failed. None of them produced anomalies that required intervention by the crew or mission control, but all of them produced data that is being analyzed with the specific goal of identifying and correcting the small deviations between model predictions and actual performance that are the inevitable product of the gap between the ground testing environment and the actual deep space operational environment. The engineering community that designs and operates these systems describes this process as model validation and update, and it is one of the most important contributions of a test mission to the program that follows it. The models that will be used to design and certify the life support systems for the Artemis lunar surface missions will be better, more accurate, and more reliable, because the Artemis II crew spent 4 days demonstrating exactly how the systems behave in the real environment. The observations that the crew made of the lunar surface during the flyby are contributing to a specific scientific question that has been growing in importance as the planning for lunar surface operations has matured. The question concerns the dust. Lunar dust is one of the most significant operational challenges of lunar surface operations, a fact that the Apollo program documented extensively, and that has been confirmed and extended by subsequent robotic missions and by laboratory analysis of the lunar samples returned by the Apollo astronauts. Lunar dust is fine, chemically reactive, electrically charged, extremely abrasive, and adheres with remarkable tenacity to any surface it contacts, including visors, equipment, and the mechanisms of the airlocks that surface crews will use to transition between the pressurized habitat and the lunar surface environment. The specific concern for Artemis III and the subsequent surface missions is the behavior of the dust in the vicinity of the landing site during the powered descent of the lunar lander. When a rocket engine fires near the lunar surface, the exhaust plume creates a supersonic flow of gas across the surface that mobilizes dust and potentially larger particles in a way that has been observed by robotic landers, and that was documented by the Apollo astronauts who described the visibility conditions during landing and the dust contamination of equipment after landing. The question of how large an area around the landing site is affected by the plume-surface interaction, and how deep the disturbance extends into the regolith affects the safety of the landing itself, the cleanliness of the airlock environment, and the conditions that the crew will encounter in the first minutes after emerging from the lander. During the Artemis II lunar flyby, the crew observed the surface of the moon at close range from a spacecraft that was itself not producing any plume-surface interaction, providing a baseline view of undisturbed lunar regolith in the South Polar region. The observations, which were recorded on the mission cameras and documented in the crew's verbal logs, captured specific surface features in the landing zone, candidates that are relevant to the dust hazard assessment. The crew observed and documented the distribution of rocks and boulders in the candidate landing areas, the surface texture of the regolith, as visible from flyby altitude, and the visual appearance of the crater rims and ejecta blankets that surround the candidate landing sites. These observations are being integrated with the data from the Lunar Reconnaissance Orbiter and from the ELSE and LADY missions that characterize the lunar South Polar environment from orbit, producing a more complete picture of the surface conditions that the Artemis III crew will encounter than was available from orbital data alone. The specific detail of the boulder distribution in the candidate landing areas is one that the crew's observations have refined in a way that the orbital imagery could not. The Lunar Reconnaissance Orbiter cameras have produced extremely high-resolution imagery of the South Polar region, resolving individual rocks down to a meter scale in the best conditions. But the viewing geometry of an orbital camera looking down at the lunar surface produces different information about rock distribution and surface roughness than the oblique viewing geometry of the Artemis II flyby, in which the crew was looking across the surface at low angles that revealed the three-dimensional character of the terrain in a way that the nadir-pointing orbital cameras cannot replicate. The crew's observations identified specific areas within the candidate landing zones where the boulder distribution appeared from the flyby viewing angle to be more sparse and more suitable for a safe lander touchdown than adjacent areas, and these observations have been incorporated into the quantitative landing site assessment that is ongoing. The human physiology's data from the Artemis II mission is being analyzed by the NASA Human Research Program, which is responsible for the biomedical research that supports safe and effective human space. The crew members wore monitoring equipment throughout the mission that continuously recorded a range of physiological parameters including heart rate, respiratory rate, movement, and activity patterns, and the quality and duration of sleep. This data, collected in the actual deep space environment and during the actual operational demands of a crewed cislunar mission, is contributing to the characterization of how the human body responds to the specific combination of stressors present in deep space. The sleep data from the mission is one of the more significant contributions to the Human Physiology Research Program. Sleep disruption is one of the most well-documented and operationally significant challenges of astronauts on the International Space Station. Consistently report sleep quality that is worse than their sleep quality on the ground. And objective monitoring data confirms that sleep duration and sleep architecture during spaceflight are disrupted relative to pre-flight baselines. The mechanisms contributing to this disruption include the altered light dart cycle in the spacecraft environment, the cognitive and physiological arousal associated with the operational demands of the mission, and possibly the physiological effects of weightlessness and altered fluid distribution in the body. The Artemis II sleep monitoring data shows a pattern that is broadly consistent with what has been observed on International Space Station missions, but with some features that are specific to the deep space environment, and that had not been characterized in human subjects before. The most notable of these features is the pattern of sleep disruption associated with the peak radiation environment during the Van Allen belt transits. The crew members' physiological monitoring data shows elevated physiological arousal during the belt transit periods, that is, consistent with sleep disruption in the crew members who are in their designated sleep periods during those transits. The causal mechanism is not certain from the current data. The elevated radiation flux during the belt transits could be affecting the crew members' sleep directly through radiation interactions with the central nervous system, or the correlation could reflect a secondary effect of the operational awareness of the belt transit, creating a state of heightened vigilance that is incompatible with sleep. Distinguishing between these mechanisms will require additional analysis of the full data, but the observation itself is important for the planning of longer duration missions, on which adequate sleep is even more critical than on the short Artemis II flight. The cardiovascular monitoring data from the mission is showing patterns consistent with the well-characterized deconditioning effects of weightlessness, with the expected fluid shift from the lower body to the upper body that occurs in the absence of gravity, producing the facial puffiness and nasal congestion that astronauts regularly describe during the early phase of the rate at which these adaptations are occurring, and the degree to which the countermeasures that the crew used, including the lower body negative pressure device that simulates some of the effects of gravity on the cardiovascular system, are maintaining the crew's cardiovascular status within acceptable ranges, is being analyzed against the pre-mission predictions. The 4-day mission duration is too short to produce the more serious cardiovascular deconditioning effects that are the concern for longer missions. But the early phase data is contributing to the understanding of how quickly the cardiovascular system begins to adapt to weightlessness, and how effective the available countermeasures are in the actual deep space operational environment. The observations that the Artemis II crew made of the Earth during the mission have generated a body of data and documentation that is scientifically distinct from the space environment measurements, but that contributes to a different set of research objectives. The cameras aboard Orion recorded continuous imagery of the Earth throughout the mission, from the initial views of the full disk of the Earth shortly after translunar injection, to the final approach views during re-entry. This imagery is being used by the Earth observation science community for calibration and validation purposes, comparing the radiometric characteristics of the Earth's surface and atmosphere, as seen from cislunar distances, with the measurements from Earth-orbiting satellites that are the primary tools of Earth's observation science. The specific utility of the Artemis II Earth observation imagery for satellite calibration comes from the unique viewing geometry of the mission trajectory. Earth-observing satellites in low Earth orbit view the planet from altitudes of a few hundred to a few thousand kilometers, and their measurements of the Earth's reflectance and emission characteristics are against ground-based reference sites and inter-satellite comparisons. The Artemis II cameras, viewing the Earth from several 100,000 kilometers away, provide a whole-disk integrated view of the planet that is fundamentally different from the regional or continental-scale views available from low Earth orbit. The comparison of the whole-disk integrated measurements from the Artemis II cameras with the concurrent satellite measurements from the existing low Earth orbit constellation allows the satellite scientists to verify that their calibration is consistent across the range of spatial scales from the local to the global, a verification that is difficult to obtain from any other source. The crew's direct visual observations of the Earth from cislunar distances also contributed to the scientific record in ways that the camera data alone does not capture. The crew members were asked to make systematic visual assessments of specific features of the Earth's appearance at regular intervals throughout the mission, comparing the visual appearance of cloud systems, ocean color, and land surface features to their knowledge of what satellite imagery shows those features to look like. The comparison of expert human visual assessment from direct observation with the simultaneous satellite measurements provides a qualitative calibration that is useful for understanding the information content of whole-disk Earth imagery, which is one of the data products that is being considered for inclusion in the instrument suite of future deep space missions that will monitor the Earth from beyond low Earth orbit. The discoveries that emerge from a mission like Artemis II are not all captured in the formal science investigations and the instrument data packages. Some of the most significant findings come from the process of encountering the deep space environment as an operational reality, rather than a predicted model, and from the mismatch between prediction and reality that is the most reliable generator of new knowledge. The crew and mission control team accumulated a body of operational experience during the 4 days of the mission that is being systematically documented and analyzed as part of the lessons learned process that follows every human spaceflight mission, and that is the primary mechanism by which operational knowledge is incorporated into the planning and training for subsequent missions. The navigation system performance during the mission is one of the areas where the operational data is producing refinements to the pre-mission predictions. Orion's navigation system uses a combination of measurements from the ground-based tracking network, which provides range and range rate measurements from the deep space network antennas, and from the spacecraft's own inertial measurement units, which track the spacecraft's acceleration and rotation to propagate the position and velocity estimate forward in time between tracking contacts. The integration of these two measurement sources is governed by a navigation filter, a mathematical algorithm that weights the two measurement types according to their estimated accuracy and combines them into the best available estimate of the spacecraft's position and velocity. The navigation filter performance during the Artemis II mission was assessed continuously by the flight dynamics team at Mission Control, and the assessment revealed a small but systematic discrepancy between the filter's predicted position, uncertainty, and the actual agreement between the ground tracking measurements and the inertial navigation system. The filter was performing within its operational specifications, and the navigation accuracy throughout the mission was more than adequate for safe operations. But the systematic character of the discrepancy, the fact that it appeared consistently rather than randomly, suggests that one of the parameters of the filter model is slightly miscalibrated for the actual deep space navigation environment. The flight dynamics team is working to identify the specific source of the discrepancy and to incorporate the correction into the navigation filter for subsequent Artemis missions. This kind of small but systematic operational finding is exactly what test missions are designed to produce. A navigation filter that performs within specifications but that has a small systematic miscalibration is not a problem for a 4-day mission, where the navigation accuracy remains more than adequate. It is a potential problem for a 30-day lunar surface mission where the accumulated effect of the miscalibration would be larger, and where the navigation accuracy requirements for specific operations, including the powered descent to the lunar surface, are more strict. Finding and correcting the miscalibration now, on the basis of the Artemis II data, is precisely the purpose of the test flight program. The question that the scientists and engineers and mission planners who are processing the Artemis II data are most frequently being asked by the journalists and the policymakers and the public who are watching the program is what the discoveries mean for the timeline and the design of the missions that follow. This is a reasonable question, and the answer requires distinguishing between findings that require operational changes before the next mission and findings that will drive design improvements for the missions further down the program timeline. The radiation environment findings require the most immediate operational response. The specific features of the outer Van Allen belt radiation environment identified by the Artemis II measurements are being incorporated into the trajectory optimization for Artemis III, adjusting the specific timing and geometry of the Van Allen belt transits to minimize the total dose accumulated during the phases of the mission, that the new measurements have shown to be more intense than the pre-mission models predicted. This trajectory optimization is within the design flexibility of the Artemis III mission profile, and does not require any hardware changes to the spacecraft. It is the kind of operational adjustment that test missions are specifically designed to enable. The life support system performance data is driving model refinements that will affect the consumables manifesting for the lunar surface missions. The specific quantities of oxygen, carbon dioxide, sorbent, water, and other life support consumables that are carried on each mission. The refined models will produce more accurate predictions of the consumable quantities needed for missions of specific durations and crew sizes, reducing the uncertainty margins that are currently built into the consumables planning, and potentially allowing those margins to be reduced as the models are validated by additional flight data. Reducing consumables margins frees up mass that can be applied to other mission objectives, a benefit that compounds as missions become longer and the total consumable mass requirement grows. The communications environment data from the lunar vicinity is informing the detailed design specifications for the Lunar Gateway Communications System, which is one of the elements of the Artemis architecture that is still in development. The multipath interference characterization that the Artemis II data provides will be incorporated into the link budget analysis for the Gateway Communications System, ensuring that the system is designed with adequate margin to maintain reliable communications in the actual radio frequency environment rather than the simplified model environment that was used in the preliminary design. The operational and human factors findings from the mission are being incorporated into the training development for Artemis III and into the crew procedures, documentation that will guide the operations of the lunar surface crew. The visual environment observations from the lunar flyby are being used to update the training scenarios that will prepare the Artemis III crew for the specific visual challenges of the South Polar terrain. The communications blackout psychological data is being incorporated into the psychological support and crew resource management training that prepares crews for the communication isolation they will experience during lunar surface operations. The data that came back before the crew did has been flowing continuously since the moment the Orion spacecraft's antenna reacquired the Deep Space Network signal. After the landing and recovery sequence was complete, the science teams, and engineering teams, and operations teams at Johnson Space Center and at research institutions around the world are working through it systematically, converting the raw measurements and observations and performance data into the findings and the corrections and the refinements that will make the missions that follow Artemis II safer and more productive, and more capable than they would have been if Artemis II had not gone and had not looked carefully at what the deep space environment actually contains 250,000 miles from Earth. The Orion spacecraft and its 4-person crew encountered an environment that the models had described in broad terms, but that revealed, in the details that only actual presence can provide, a series of specific features that the models had not fully captured. The radiation environment in certain regions of the outer Van Allen belt was more intense than the pre-mission predictions had indicated. The communications environment near the lunar limb showed multipath interference features that the relay system design will need to account for. The life support systems produce consumption data that has refined the models used for long-duration mission planning. The visual environment of the lunar south polar region, seen from a crewed spacecraft at flyby altitude, provided observations that orbital imagery had not fully conveyed, and the psychological and physiological data from the crew during the communications blackout and the radiation belt transits is providing the human factors baseline for the more challenging missions that will follow. None of these findings represents a discovery in the sense of a completely unexpected and transformative revelation. They are the systematic refinements, the model corrections, the operational lessons learned that are the specific and intentional product of a test mission conducted in an environment that had not been directly measured by human-occupied spacecraft in more than half a century. They are exactly what the Artemis II mission was designed to produce, and they are exactly what the Artemis program needs to build the foundation for the lunar surface missions and the deep space missions beyond the moon that the program is working toward. The commander who watched the record fall while looking out the window at the Earth has been spending the week since the splashdown in the debriefs and the interviews and the technical discussions that are the institutional aftermath of every significant space. The process of transferring the knowledge and the experience accumulated during the mission into the permanent record of the program. He has been asked, in these contexts, what surprised him most about what Artemis II found at 250,000 miles from Earth. His answer has been consistent. It was not any single measurement or any specific observation. It was the general character of the deep space environment, as encountered by the people actually present in it. The way that the environment was simultaneously more ordered and more variable than the models had suggested, more precisely structured in some respects, and less predictable in others. The way that the combination of knowing what to expect and encountering the actual thing produced, every time, something slightly different from the expectation. This is what exploration has always been. The territory that exists between the model and the measurement, between the prediction and the reality, between the map and the ground. Artemis II spent 4 days in that territory and brought back data that is changing the map for the missions that follow. 250,000 miles from Earth. The spacecraft and its crew found what missions to new places always find when they look carefully enough. Not what anyone expected exactly. Something better. Something real. The data started coming back before the crew did. That is how it always works in deep space missions. The telemetry stream and the science instruments and the recorded observations flowing back to Earth through the deep space network antennas in the hours and days after the mission, while the astronauts are still doing the work of coming home, still managing the re-entry procedures and the parachute deployment and the recovery sequence that ends every crewed space in the controlled drama of a splashdown in the Pacific Ocean. The mission controllers and the science teams at Johnson Space Center and at the research institutions that had contributed instruments or investigation objectives to Artemis II were already processing the early data while the crew was still in the water, still being helped aboard the recovery ship, still blinking in the unexpected brightness of the Pacific afternoon after 4 days in a vehicle whose windows frame a sky that is not blue. And what the data was showing, in the initial processing that began within hours of the mission's end, and that deepened over the following days as the full dataset was downlinked and organized and began to be analyzed properly, was producing, in the measured language of scientists who are trained to be careful about what they claim before the analysis is complete, a series of findings that none of them had expected to be quite as clear or quite as significant as they were turning out to be. The radiation environment at 250,000 miles from Earth was not a surprise. In broad terms, the scientists who designed the radiation measurement suite aboard Orion had built their instruments around models of the deep space radiation environment. that had been developed over decades of unmanned spacecraft observations, refined by the measurements from the Apollo missions, and updated by subsequent robotic missions that had passed through or operated in the cislunar environment. They expected elevated radiation compared to low Earth orbit. They expected to see the signature of galactic cosmic rays, the high-energy particles that stream into the solar system from outside it, and that the Earth's magnetic field and atmosphere shield us from on the surface. They expected to see the variable contribution of the Sun in the form of low-energy solar energetic particles. What they did not fully expect was the degree to which the passage through specific regions of the cis